In this problem, our job is to find the location of an object M3 where the net gravitational pull on it from M1 is balanced by the gravitational pull on it from M2. To do this, the trick is to recognize that if our job is to find x, the distance between M1 and M3, then knowing the distance between M1 and M2, we can write the distance between M3 and M2 as 20 minus x, so as to not introduce an extra variable. If the net gravitational force on M3 is going to be 0, then the force of gravity between M1 and M3 is going to be equal to the force of gravity between M2 and M3. Plugging into Newton's law of universal gravitation, we get G M1 M3 over the distance between the centers of M1 and M3, which we called x, and that's squared. That's equal to G times M2 and M3 over the distance between the centers of M2 and M3 squared. Looking at what we have here, you can see that the universal gravitational constant on each side cancels out, and the mass of object 3 cancels out, which is why that was not given. Looking at what's left, we now have M1 over x squared is equal to M2 over the quantity 20 minus x squared. Plugging in our values for M1 and M2, which scrolling up here, you can see that M1 is 2,500 kilograms and M2 is 625 kilograms. We have 2,500 over x squared equals 625 divided by 20 minus x quantity squared. From here, it makes sense to square root both sides. So if we square root 2,500 over x squared, we should square root the other side to keep the two sides equal. And when you square root a fraction, you square root both the numerator and denominator. So the square root of 2,500 is 50. The square root of x squared is x. Square root of 625 is 25. And the square root of 20 minus x quantity squared is just 20 minus x. Cross multiplying, we get 25x equals 1,000 minus 50x. Adding 50x to both sides, we get 75x equals 1,000. So x is equal to 13.3 meters. And that is the distance from the center of M1.